Yes.
Ken is here.
There we go.
All right, go.
Take it away. Okay. My name is Ken Krechmer. I've been lecturing at the University of Colorado, or in this case, virtually at the University of Colorado for over 20 years. And it's been a pleasure every time. And so I have looked forward to this one as well. Thank you, Ellen and Mark, for inviting me. I lecture on a subject that probably most of you have heard little or nothing about, and don't even consider it quite a subject of relevance, the isology, the science of references, standards, and standardization. And that sounds terribly boring, and I hope to explain that it's not. Oops, why is my slide moving? Let's try that. There we go. Okay, so since I said this is the study of references, standards, and standardization, let's define those words. A reference is the basis for comparison. In that sense, it's the fundamental unit of information. The bit is a reference. So a reference is, in fact, more fundamental than the term bit. And so a standard is a codified, quantified reference imposed by something, an authority, which might be a government, a committee, the market, the company. How the standard is imposed varies widely, and it's a source of significant market issues. And this goes back to Hayek, who's an economist, famous Austrian economist, in his book Rules and Order, 1973. Standardization now is yet more complicated because it refers to either the creating of a standard, the implementing of a standard, or the using of a standard. If the people who write Linux, who created Linux, basically were the creators of Linux, which we now know of as a standard. On the other hand, if in an organization or a product we decide to implement Linux, we are standardizing on Linux in our product. And we are implementers of that standard. We didn't write the Linux standard. And on the other hand, if I am a user organization and I decide that all my computers' operating systems will be Linux based, then I am using that standard. I didn't implement it. I didn't create it. But in each of these cases, it's common to hear people say, we are standardizing. And so again, the terminology is treacherous. And that's part of the problem with understanding this field, is all of these words are used in multiple ways. To take this from a fun side first, the history of technology can be seen in its standards. And of course, in the beginning, standards are not exactly called standards, they're called references. We don't have the concept of an authority that defines a standard very early, although there's a little bit of it emerging. As always, this is very evolutionary and things emerge. The change from animals probably over here somewhere to humans, which begins here, is the beginning of speech and communications beyond what a herd might have. And so we can actually see the beginning of humanness as the beginnings of a set of symbols, either sounds or pictures or hand gestures, whatever they might be, that allow greater communications. And the purpose of this communications is a little bit trickier than what animals do. The purpose of this communications is to barter. Because it's recognized quickly, the human mind has amazing skills that one area might have good flint, but another area might be able to grow things or find things that were growing in that area that are unique. A berry as example. And so trading their one area's berries for another area's flint might be a very valuable technology, a communication skill to have. And such bartering requires, symbols. How are you going to do this? And so we start creating hand symbols, we start creating gestures, we start creating sounds, and we begin what becomes human behaviors beyond animal behaviors. And that's bartering. And when that emerged, obviously that emerged over very, very long spans of time. But that is the beginning of what we now call symbols, which are numbers, stop signs, all kinds of road signs, alphabets, et cetera, et cetera. They are ubiquitous in every human society, symbols. So we really recognize that they are fundamental. And those symbols, as we know them today, are standardized. The most successful standard in the world ever is the Arabic number system. Every civilization uses the Arabic number system. And think about the significance of that standardization effort and how long it took and how many people got upset about the fact that their number systems were not the ones that were appropriate. And even more so, think about the fact that this is the basis of what we call mathematics. And so symbols actually emerge before the concept of mathematics, but mathematics is, in fact, the basis of this history of technology. Symbols are elements in a set. Measurements are how you determine the members of a set. And the complete set is a design, a something. All those symbols together represent something. And I've used the term design because I haven't thought of a better one. So references are the basis of this concept of a set. And then standards, you'll see, are also the basis of the concept of another form of sets. So from bartering somewhere around 10,000 BC, we start to get into what we call civilizations or settled communities. No longer animals moving in a terrain to gather or hunt whatever they can find in that area. We start to evolve into settled communities. And if you settle in a community, it quickly becomes important to make measurements. If you're going to grow something, which is the big reason for having settled communities, you need to measure an area and count, which is the simplest form of measuring how many seeds you put in that area to feed how many people. So these concepts of measuring start to emerge with the agrarian society around 10,000 BCE. So measurements then are the first form of references, and quickly we move into the concept of sets of measurements, which become designs, and those designs are so monumental that they are monuments. The pyramids, the Hanging Gardens of Babylon, the Colossus of Rhodes, the seven wonders of the world. None of them were the Grand Canyon, or the Alps, or natural wonders. They were the creation of human minds. The idea that we could draw something in sand or on papyrus and build it as a design. And the pyramids are, by their very shape, the conception of the design is the most important thing. You didn't create the pyramids by just piling rocks on each other. You actually had to understand the design first. And all the seven wonders of the world were designs. And they basically represented the amazing concept that human beings had, that they could take measurements and make them into designs. And that was the beginning of our modern, successful, large civilizations, was standards, as always. Standards, because they represent the basis of mathematics, are the basis of everything. So after designs, it's interesting to see that the next iteration is manufacturing, the Industrial Revolution. And it happened way earlier than is currently thought. It was not related to the steam engine or the mining of coal or any number of other things that people have thought. The first place that manufacturing emerged, and let's talk about what manufacturing is. Manufacturing is the result of repetitive processes, making something over and over and again the same. And so that began in the 1400s in Venice, Italy. And you can actually go there now and to the Arsenal, which was the world's first manufacturing plant. And Henry Ford basically copied it. It is linear. The galleys went down a long, thin building, and they were built. And you can actually see carved into the stone floor of that building, of one of those buildings, the shape of a rib of the galley, the actual shape. And they standardized without even understanding the word standard, but they did it. All the oars, the oarlocks, the sizes of ropes, the sizes of pulleys, on and on. That was their significant strength. And they actually divided up the arsenale into different areas where they did the rigging work and where they did the mast work and where they did the hull work, where they did the oar work. Those were all specific areas. This concept of doing things over and over and again, success to produce something, was unbelievably successful. And how unbelievably successful? In Corsica, which is a similar latitude, they produced a galley in a year, one galley in a year. In the Arsenal, they produced one galley in a week. 50 times as successful. Needless to say, this had enormous economic consequences because it allowed a very famous family called the Medicis to control trade on the Mediterranean. The Mediterranean was the seat of the world's wealth, much of the world's wealth, and controlling trade produced unbelievable wealth. And they were, at the time, far and away the wealthiest family in the world. So you start to see, I hope, the idea that the concept of standards is very closely connected to wealth, the expansion of value in society. So looking back, we have bartering. Measuring is the agrarian revolution. Manufacturing is the industrial revolution. And now around 1800s, we start to have networks, the first ones being rail, or actually before that, road. But the first ones that we can kind of think about more clearly as standards are networks. And those were rail. And the concept now of a standard starts to get much more important. And our information age emerges. And I'm proposing with an idea here, because the history is still too new, that around 2000, the concept of openness emerges. And openness meaning that we have the ability to communicate openly. We're much more transparently. There's a lot of words we're using in our society now that are basically about being more adaptable. And not only as human beings having more of an ability to accept all the variance that might allow, but as networks allowing all the variance that might allow as well. And that's what we want to talk about, and because that's where the future is going, the ability to be more open. So the wonderful thing about this history of standards is it gives us some ability to see in the future. Because we have the basis of mathematics, we have the ability to foresee the future. If you will, there are two kinds of people who foresee the future: mathematicians and charlatans. And you can pick who you'd prefer to listen to. And everybody else has an opinion, but that's probably not very useful, including mine. But if you have a set of mathematics, you actually have some ability, a very limited, most often, and very narrow, almost always, to actually see into the future. If you understand the mathematics, where the rocket will hit has some likelihood because of the mathematics that you understand. It has nothing to do with anything else. So let's go forward. So I use these words here, similarity and compatibility, but once again, they're very messy. So our plugs here, if I draw a vertical line between plug 1 and plug 2 with my arrow, with my pointer, that line represents similarity. And over here at the socket 1 and socket 2, the vertical line represents similarity. However, the concept of the plug fitting into the socket, that is compatibility. It's only this outline here that represents the same as this outline here, or the same within a tolerance. And that's compatibility, that form. Quite different. Similarity and compatibility are extremely different and extremely confused. We have a patent system as example, which is designed to allow people to control the production of similar plugs or similar sockets. And that's what it was designed for. And it is now applied to control compatibility, which makes a lot of people very upset. But our legal system, our patent system, does not understand this drawing. It's too complex for them. So that is the reason. That is the basic reason why, as example, the pharmaceutical industry, which invests large amounts of money in trying to understand some drug or some process and make it similar, manufacture it the same over and over again, is extremely supportive of patents, because it allows them to make these enormous investments. And the communications industry, which is being quite often held up for ransom by patents on that are I have patented the plug and therefore your socket has to pay me kind of concept, which is unfortunately allowed under the patent law, because the people who have created the patent law don't understand the difference between similarity and compatibility. And it's also worth pointing out in that same discussion that the idea of patents emerged in Venice, Italy, around 1500. The very first patent occurred around 1500 in Venice, Italy. It wasn't called a patent, and it wasn't called a royalty. I think it was a fee, if your translation from Latin is good, which mine is not. And it was a letter, which the term patent letter is still used. But it was a letter basically from the local government saying that if you can create a better device or shape or something for us, we will let you have a payment for it for some span of time. We will give you a payment for some span of time. Okay, so with this very significant but subtle idea of the difference between similarity and compatibility, let's go on and look at the successions of references and standards which we talked about from a history standpoint. Now let's talk about it from a how it works standpoint, some of which I've already done. So symbols are number systems as example, and the purpose of a symbol is to identify, and it promotes bartering. And measurements, we have units of the pharaoh's forearm is a cubit. King Henry's foot is a foot. The measurements were recognized, the important, very significant, fundamental to the power that be. And they quantify things. Another place measurements occurred early, they're carved into various stone in churches or monuments, so that people could bring up whatever they had and measure them accordingly. The taxation systems, there's an interesting model change up through design. Basically, the taxation did not exist very much, and what was done instead was plunder. You would attack some other society and plunder their value, whatever they had of value, and bring it back to your own. When you have measurement, you start to be able to tax things. And so if you have so many of this, which is a count of the simplest form of measurement, or some length of that or weight of this, you then tax it. And there were tax houses throughout the world where the local authority required all trade to be brought to the tax house, where the tax was levied based on some metric, again, a standard of measure. And there's actually a log of a ship's captain, which I saw a copy of in the 1600s, where he marks in each port the differences in the measuring systems that were applied, so that he had some idea of how much taxes he would have to pay, and therefore how much value he had to bring with him in order to pay them when he traveled to various different ports. And so he actually marked in his log which different town had which different taxation mechanism. And it's a complex code, but people have figured it out, of weights and measures, basically. So as we talked about in similarity, we have the amazing example of the Venetian galleys and how successful they were, and they promote manufacturing efficiency. And let's talk a little bit about manufacturing efficiency, because it's amazingly powerful. The Industrial Revolution was not a small potato of advance of civilization. When you manufacture something the same all the time, as the Venetians discovered, you gain significant efficiencies. And we argued they're maybe 50 times as efficient. But on the other hand, let's take a barrel. If you make a barrel and you make by standardizing the barrel, you enhance the efficiency of your manufacture, let's say by the same 50 times. The next thing that happens is when the barrel is moved onto the cart to transport it, you create holes in the bottom of the cart that the barrel fits into. So your process of strapping on the barrel is less complicated, and your cost of transport is reduced. And then when the barrel is moved to the bar, there's another hole in the top of the bar where the barrel sits, so that we have efficiencies in the use of the barrel, as well as efficiencies in the transport of the barrel, as well as efficiencies in the manufacture of the barrel. So this industrial revolution was the process of distributing amazing efficiency out by virtue of creating what would be called standards. When a manufacturer does something the same way every time, they call it a specification. When an authority does it, some group of manufacturers, let's say, then we might call it a standard. And if we just do it, but don't even acknowledge that we're doing it, like the shape of arrowheads or the shape of hand tools, those are just references. So now with compatibility, we have railway gauges, group 3 facsimile. A lovely discussion is Gillette. it is commonly talked about that Gillette is a business model of give away the razor and sell the blade. In fact, that's incorrect. Have you ever wondered why the blades of a Gillette razor have this funny triangular, square, rectangular form in the center of them? How could that, what's the purpose of that? Turns out that is history of standards right there. When Gillette started giving away his razors and selling his blades for a very handsome price, he had a couple of things going for him. He was obviously a very smart man. He actually understood that a certain alloy of metal and a certain technique of sharpening it produced a better blade than anybody had done before. And he had figured out how to do it at low cost. And so he came up with this very clever idea of giving away the razor and selling the blade. Not very surprisingly, when he was successful with that, which he was very quickly because it was an excellent solution technically, his competition immediately started to sell blades cheaper than he did because they didn't have to pay for the damn razors and give them away. This obviously caused Mr. Gillette some significant upset, and he tried almost immediately to patent his razor blade, but he had already patented the technology, and his competition basically was dealing with the fact that it's hard to tell when you look at a blade which one is sharper, and so they claimed that their blade was as sharp as his. And so they sold it for less, so people bought it. So he then wanted to patent the shape of the razor itself that held the blade. And that was originally a little rectangle inside the blade that just held it in place. It's all it needed. But when he took that to the patent office, they said that, and we have this documentation because he filed for patents. They said basically you can't do that. It's just a shape. Sorry. So he tried to make the shape more complicated. The patent office was still shapes are shapes. Sorry, we don't patent them. So somebody came along with a brilliant idea. He could trademark a shape. And again, we have this documentation. And he sent to the trademark office the request to trademark a more complex shape, which interestingly enough was designed so that a razor that his competition was making would not work in that shape. So we can actually see the competition's form factor of the holes so that he made it different. The first time he tried it, it wasn't different enough. And the trademark office says that's still just a shape. And we don't trademark it. Then he made it yet more complex. And again, more complex in such a way that it wouldn't work. The razors of his competitors wouldn't fit in it. And then he started giving away these razors, which he was able to trademark. And then he sued the manufacturers who copied his trademark shape and prevented them from selling into his market, and thereby became successful. So this is a big thing to understand. This is fundamental to the starting of any company. You have to have a value, a new technology that works better than something before. Yes, absolutely. You have to have a market, people who say, I agree with you that technology does something that I want and I'm willing to pay for. And you have to have control. All three. You have to have the product, the market, and the control. Then you have a successful company. And even if you're a cornered grocery store, your control is that corner. That geography is what is yours, and the people who are near to that store will be your customers. And that's how you try to control your market. And we lose that an awful lot in starting companies. The question of how are you going to control what you offer that's better? And many companies more recently have emerged who do not have control without the beginning of network effects. So as Google starts out, they're a search engine, and anybody can create a search engine, probably a pretty good one in the case of a number of people. But the search engine who comes first then has an inordinate advantage because they get to be the biggest database of search functions, search data, and therefore other people want to use it. So the network effects model expands. And so Gillette you don't really see the network effects, but as example, in telephone systems compatibility, you do. The very first Alexander Graham Bell telephone system was installed between a doctor's office and a pharmacy. The doctor had reason to pass information to the pharmacy or get information from the pharmacist about what was available for his patients. Now, in this case, if you were another doctor or another pharmacy, which phone would you buy? Only one, the one that worked between the existing network. That's network effects. Once the network exists, it is extremely unlikely that anybody will choose not to use it. The network, if it has any value at all, you will want to use it. And so network effects becomes the dominant form of economic model in compatibility standards. It's why compatibility is so economically significant. And why, of course, then that patents, which were designed for similarity, are instead applied to compatibility. Again, the economists will tell us whenever you create a value system, it will expand to fulfill as many possibilities as it can. Blockchain is an extremely good example. So now I propose we're moving towards adaptability. Originally, modem handshakes, session initiation protocol, group 3 facsimile T30, which was a negotiation mechanism, RACF, which is a internet negotiation mechanism. They negotiate variation and they provide greater openness. So let's head to another slide. So summing up, similarity creates efficiency, compatibility creates network effects, and adaptability has the opportunity to reduce network effects, which is not, so as I've talked about, compatibility is not well understood. Even though it's been around since the 1800s, it's been a big deal since the 1800s because it was the King of England who said the rail size was going to be 4 feet 8.5 inches. It was a very big deal. There were rail sizes that were larger, where they wanted to carry large loads over flat land, and there were rail sizes which were smaller, where they wanted to go into caves or up mountainsides. And the recognition of the need for a common rail size became so great that it was directed to the king to make a decision. And the decision was an economic decision. The most common rail size was 4 feet 8.5 inches. And now adaptability can reduce network effects. There were actually railroad cars made with double trucks, where there were sets of wheels at different grades to allow the passage of a train on different rail gauges. So the internet, interestingly enough, has a little different idea of compatibility. So this basically, the vertical direction is the layers of the OSI model, or in this case, the internet model, which is a 5-layer model, which we'll talk about a little bit if we have time. But in the center of the model is the IP layer 3 and TCP UDP layer 4. That this concept, by the way, this drawing comes from a MIT professor by the name of Dave Clark, who was one of the early developers of the internet, and who recognized that what was being done was all the communications forms would be compatible with the IP layer, and all the application forms would be compatible with the TCP UDP layer. And as long as you kept these two layers in the middle a constant, every application and every communications could operate over it. And there were enormous arguments. I was involved with a lot of them about whether communication should be packet-based or circuit-based, and the values or disadvantages and advantages and so forth. But eventually, because of the success really of semiconductors and integrated circuits, the TCP IP model won out. So in the OSI model, we have 7 layers of standards: a physical layer, media access control, transport, network, session, presentation, and application. These higher layers above the TCP UDP are often called service discovery protocols in the internet language. In circuit switch languages, I've used the term etiquettes for protocols, sometimes stacks all the way up. And in the internet languages, IETF languages, network discovery protocols is the common term. So the internet, by the way, does not use either layer 5 or layer 6. Those are not employed in the network, and they are, in fact, part of the application. Because we don't have layer 5, which is session, when we don't have session, we don't have security. And so if we can't say, I am talking to you now, and I will stop talking to you at the end, we don't have control of our definitions of who's talking to whom. And so introducing that strictly in the application and not in the network created the very interesting situation that we have today, where the ability of people to send whatever they like without any real concern for their identity causes problems. It certainly causes advantages, and whether the problems and the advantages are better or worse is being determined. At the 6th layer of standards application, we have similar related problems where voice codecs and video codecs are often incompatible or produce various differences that we find difficult. It's looking at the various faces in real time, it's getting better. When I first started doing video, it was pretty treacherous. And there's been a long passage towards trying to resolve it. Unfortunately, the way of resolving it is to produce common protocols. And the common protocols may well be ones that are not patented, which may well be not the very best technology. And so that we're dealing with those issues. So resource allocation function I mentioned earlier. Again, this is an internet function, which basically negotiates adaptability. Forms of security, whether it's authenticity, confidentiality, permission, or tracking, all need to be negotiated. The word security, as this points out, is bandied around quite often by people who don't have a good idea what they're talking about. And it needs to be broken into authenticity, confidentiality, permission, and tracking, so that you have some idea of what you're making secure. And then adaptability, which is the term I've used, is the peer-to-peer option and function negotiation that can occur with resource allocation. And there's another protocol called SIP, Session Initiation Protocol, which is designed to fill in that lack of the layer 5 and mechanize a session connection between the applications. So putting that into the architectures, here we have the third layer and the fourth layer, TCP, UDP, and the third layer, IP. An etiquette could be, it's a general term, anything all the way up and down. Etiquettes really emerged, or I've used the term in T30, which is really a 7-layer stack of whatever you want, we'll figure out how to do it, negotiation. This is a model of the names of the internet layers: physical, media access control, network transport, and application. And then you can see the service negotiation protocol fits above that. It's a network identification protocol. I'm sorry, it's not. It's a service identification protocol as opposed to a network identification protocol, which would be down here. And session initiation protocol obviously sits above the transport. So the idea of open standards, which is part of this concept of openness. Today, standards are usually created by commercial organizations. It's no longer King Henry's foot or the Pharaoh's forearm. Commercial organizations want to control their markets. Google controls its market by Google APIs. If you want to interact with a Google database, you have to use Google APIs. If you want to interact with the Facebook database, you have to use Facebook APIs. If you want to interact with the Amazon Web Services cloud computing, you use Amazon APIs. And there's a big argument going on, really looking for market success and market control, where these various different organizations, none of whom really understand adaptability very well, are trying to assert their API versus others, and at the same time trying to support their customers who would like multiple different API support. And that negotiation process is active as we speak. Any number of the people on this call are probably smart enough to write adaptability protocols that negotiate between the multiple APIs and make them great sums of money if they can figure out ways to control them, which if you read some of my papers, the ways of control are available. So open standards are a way to reduce commercial control. And the more adaptable we make things, the more they can be open. However, we can still allow commercial control. An adaptability mechanism can pass an ASCII representation of a trademark name between the ends of a system. So if I have a very clever way of updating the software in my automobile, a company named Tesla comes to mind, I could obviously keep the code hidden so that no one sees it, but that's not too good because a number of people could probably figure out how to reverse engineer that code. It would be difficult, but given the number of good Chinese engineers, it's not impossible. So the way to do it would be if Tesla sent the ASCII representation of Tesla to over a standard interface to the car, where all cars had this standard interface. And if the car came back with the ASCII representation of Tesla, then the two ends would know that they could now be proprietary and do whatever Tesla wanted to do, which was, if it was better than other car manufacturers, great. And when General Motors was passed, ASCII representation of General Motors was passed back and forth, if that was better, then people would use it. And so we could actually have standards which negotiate commercial control. And users then would be in the business of saying, oh, I like what this company offers better than what that company offers, and I'm willing to pay X extra for that capability. And I would have both open standards and commercial control. A very powerful concept for the future, which could be applied to APIs of any type. making them far more desirable and successful. Successful in the sense that not only do they make the manufacturers money, they provide more value to the users. So we can think about open standards in this way. Each different, if you will, grouping, implementers, users, government, has their own interests in openness. The implementers want a single process for worldwide standards and a fair means to negotiate intellectual property rights. I don't want, as a manufacturer or software developer, I don't want somebody to come to me and say, oh, you did this, it's going to cost you so much. No, that's not the way I want it to work. I want to be able to go say, if I do this, how much is it going to cost me? And that's not the way the system works today. And implementers realistically get very upset when some lawyer sends them a letter saying, since you decided to do this, it's going to cost you this. And so the standards bodies around the world have started to create lists of who has intellectual property on specific standards. So the manufacturer can then look at the list and say, if I do things this way, it will cost me this much. On the other hand, he can also say, if I provide a proprietary functionality and nobody else then gets it, I can control my market. And I don't have to license my proprietary technology unless I wish to. And in fact, this occurred in the Group 3 facsimile market. That Group 3 facsimile was done with the protocol called T30, and different fax manufacturers, predominantly Japanese companies, developed more successful proprietary technologies than the standard at any given point in time. And they did that on purpose. And they licensed those technologies for significant economic value to companies until eventually the standard came out, standardized it. These Japanese companies were extremely wise in their operation. Once the standard came about, they licensed the technologies for very low cost and then started developing the next technology ahead for the next standard. RICO particularly did this successfully throughout their career. And amazingly enough, I've spent a good deal of time talking to RICO engineers, at least the ones who spoke a language that I did. And none of them understood that this is how RICO had made money. They did it, but they did not recognize that what they were doing. It was a series of individual decisions as opposed to a conceptual development. At each time individually, they could see that they should license something. They could see that their engineers made a better fax machine than before, but they never thought about it as a process of making a strategic decision for the company over a long span of time, because they didn't really understand standards, even though they went to every standards meeting. Very interesting. So this kind of gives you an idea, and I'm surely running out of time, but maybe I should leave a little time for questions. So this is what we're trying to talk about. A fair interface balances legitimate public good with legitimate private gain. I absolutely disagree with organizations like the W3C who say that if there is legitimate private gain, that's too much. They want free standards, free technology. As an engineer, I have made a very good living over the years by providing people with ideas which they chose to charge for. And by virtue of doing so, paid me handsomely. And I was very happy. And I wish you all the same. So, as we talked about, we could create APIs. They don't really, we could create, adaptability. 5G has a lot of different kinds of adaptability, but there's nothing as adaptability as a function, as a negotiation process in it. Blockchain obviously would be greatly enhanced by mechanisms that would allow for multiple different kinds of systems. That may not be possible if you use the processing power as the weighting that establishes control. And that looks to me like a very fundamental problem with some of the concepts of blockchain, but there are people who are thinking about how to reduce the processing power as a mechanism of market control. Vehicle-to-vehicle communications, extraordinarily important. The idea that we will have intelligent vehicles that will drive around without human intervention is quite silly, and irrespective of who it might come from. On the other hand, vehicle-to-vehicle communications will give drivers capabilities that they do not have now. Once those standards exist, to be able to see the vehicles that are not seeable, and recognize what's happening, to be able to understand road hazards or all kinds of things that might be identified. Vehicle-to-vehicle communication standards, a huge area. Because vehicles are so long-lived, we badly need adaptability mechanisms so that they can evolve over time and still be backward compatible. Same with the Internet of Things and security, and we've already talked a little bit about cloud computing. Okay. Thank you. And if anybody has questions or comments, I'd be delighted.
So there was a question in the chat, which I think came directly to me. Ram, are you here?
Yeah.
Yes.
Hi, Ken. Thanks for a great talk. Let me turn on my video. You started the talk with a very interesting topic about open source and open standards, I guess.
Yes.
Can you talk about what is sort of the driver? Why is it now catching so much fire and just taking off? What's behind that?
Well, I think the history of technology is my opinion of the driver. Maybe I should go back to that slide. That one. So I'm suggesting here that the normal course of the history of technology based on standards gets us to the point where we can start to think about being adaptable. Education is a process of becoming more adaptable. We learn to speak new languages is an obvious way of educating ourselves to be more adaptable. Travel is a way of becoming more adaptable. We learn to how different cultures relate to the ones we are familiar with. And now we have computers which are complex enough, multi-layered enough, that we can start to support adaptability. And with a lot of proviso, I'm thinking that openness is the future. And I believe it's strictly, by the way, I put openness at 2000 because in that year, in 2000, was the first time a smartphone connected to a smart network, the internet. Before that time, basically, the phones were connected to a dumb network, the telephone system. And it was right there. I actually found something which indicated that it was actually that in 2000. But whether you want to argue that it was 1998 or 2002, I'm not going to arm wrestle. The idea that we could create a smart network that connected to a smart device, that's the beginning of we could be open. When devices are not smart or networks are not smart, they're fixed. They're not open.
I would
That's
bet
my
that
thesis.
I would bet that the dates are more like the mid 1960s for some of the stuff, but that it doesn't, not so much in telecommunications, but in other fields. You
Yes.
start to see the germs of open systems, and then they became widely understood when they became in everybody's pocket, as our phones now are.
Right. Yes. Yeah. There's
So,
no
for
question.
example,
My terms are vague.
Yeah, no, my PhD advisor was a Dutch architect who was instrumental in starting a a theme called open building systems, open building. And the idea was, how do you make structures compatible so that you're not locked into one manufacturer's windows and doors? And how do you allow things to vary and produce high variability and high adaptability and high flexibility over the lifetime of a long structure, like a building which might last 30, 40, 50, 100 years.
Right. Excellent.
And that was the early 60s.
Yep. Yep. Okay. Yeah, perfectly reasonable. What we're talking about here is layering is fundamental to an evolutionary system. If we look at the genetics, what we basically see is the layered system that produces evolutionary processes. And so if we look at these layers in a different context, they have different time relationships. Absolutely. More comments and questions. And Ram, was I successful in providing any sort of an answer?
Yes, but it's a big topic and I don't want to hog the time asking all the questions. So.
Okay.
Well, if there's no other questions, I'll ask one more on the same topic. Is
okay.
Because I worked in one of these big companies that you mentioned, right? So
right.
How does open source, work with commercial interest for a company to make money? There's a certain tension there, but there's also a certain sort of synergy there.
Right.
Can you talk about that?
Sure. A gentleman wrote a paper called Cathedrals and Bazaars, where he tried to contrast the idea of open source with the idea of fixed code. In his generation, it was IBM systems. And I wrote a paper in kind of rebuttal, or I guess more extension, which was titled Cathedrals, Libraries, and Bazaars. So that the way a library now is neither the bazaar nor the cathedral, it is curated. And so what gets into the library has some control. A company called Red Hat did exactly that. They took open source Linux and curated it so that it was available in a maintained and supported form for users who wanted it. And that was their model of how to gain value from an open system. I suggest that you could also gain value by having an open source, which required some sort of a economic negotiation, and said, you can use my open source, but you can only use it if you provide some value. That value might be enhancements, or value might be use, in which case use might be paid and enhancements might be judged in some way, and either give it and allow that user to pay with enhancements versus dollars. So another technique. These are all basically adaptability mechanisms, trying to subdivide user populations into different categories and figure out ways to achieve value from those categories that are appropriate for those categories. Lots more chat stuff. Should look. Oh, okay, Mark. Good. Open building. All right. Cool.
Wow, Tunde.
Okay. Any more comments?
All right.
Otherwise I should be leaving. I've got an appointment in about 20 minutes.
Yeah, I've got one about 3 minutes ago.
Sorry.
It's delightful. Thank you for doing this. This was a lovely talk. I'm happy that it was recorded, so people want to review it later. I look forward to more.
Oh,
I
me
loved it.
too. Me too, as
All
you
right.
know. Thank you,
All
Ellen,
right.
again, and Mark both. Yes, take care.
I have to find the leave button.
I can kick everybody out.
The curse of having two displays and never knowing how they're organized. All right, I'm out.
Bye.